Right, so I'm going to work through questions. This is from chapter 3.9, and these are homework questions. This is doing the work required to lift something. So what I'm actually going to do is I'm going to skip around, and I'm going to do questions 39 and 42 first. They're the ones that are most similar to things like final exam questions. Okay, so in question number 39, we're given the weight density. Let's actually read the question itself. So question 3.9. So 39 says, we have a rectangular tank that has a length of 20 feet, a width of 8 feet, and a height of 30 feet. And the tank contains water up to a height of 10 feet, and the rest of the tank is empty. Find the amount of work required to pump all of the water to the top of the tank. Okay, I guess we can also assume we're going to be pumping it out of the tank too, because we want to be able to displace it. Right. We're given the weight density of water is 62.4 pounds per cubic foot. Okay, if it's in pounds, that's actually like our force units. We don't have to take into account gravity. All right, so now the first thing I'm going to do is I was given dimensions for this. I'm told this is a rectangular tank, which is 20 feet by 8 feet by 30 feet. And we want to be able to calculate the work required to pump the water out. In real life, by the way, we would have the hose at the bottom so that we wouldn't actually have to exert work in order to get the water out of the top. But let's pretend. All right, so I'm going to make a rectangular tank. I'm going to draw this out first. First my cube. Okay, so my tank is 20 by 8 by 30 based on the dimensions that they told me before in terms of width, length, and height. And we're told that there's water up to 10 feet. Okay, all these things are important. So I'm going to use this. I've got water that I want to be able to pump out of the top. Okay, so our work, okay, is our force times the height, okay, that we're actually going. And the bounds of integration are how much water, like what's the water volume that we're actually doing. So I have 0 to 10 gives me the bounds of integration because that's how much water I have and how much I need to actually the volume of water I want to be able to take out. So let's think about things first. So our force is going to equal volume times the weight density. Okay, so our volume is length times width times height, and then we have times our weight density. Okay, so our length times width, right? The length times width is 20 times 8. We were given that before. And then our height that we're doing each sliver, remember we're going from 0 to 10. The height, each sliver, each rectangle that we're doing is a height as a thickness. This height here that we're talking about here isn't the height of the tank, it's the thickness of that tiny little sliver of water that we're taking up. So that's dy. And then the weight density we were given at the very beginning is 62.4, okay, pounds per cubic foot. All right, so keep this in mind. So this is going to be 160 dy times 62.4. We're going to plug all these things in here. All right. So equals, we're going from 0 to 10. So we did our force, right? So this is 160 times 62.4. And I've got the dy. Now the height that I need to be able to think about, the height that I need to go is, well, the whole total height of the tank is 30 feet, right? But the slice of water that I'm looking at the bottom has to go all 30 feet. And the slice of water here at 10 feet only has to go 30 minus 10, right? So I have to be able to take into account that the height that the water is at is going to be variable. It's going to vary as a function of where I'm at in the y direction, okay? So I'm going to say the height that the water needs to go is 30 minus y, okay, because it's 30, my total height, minus wherever we happen to be at the time. That's the height that we actually need to go, okay? And this is all times dy. So I can multiply everything through, and then I can distribute, because this is 160 times 62.4 times 30 dy. I'm going to integrate from 0 to 10, so I'm going to get 2,99520 dy, just a number, minus from 0 to 10, right? I'm going to multiply all these numbers out times y, or this times y, and I'm going to get 9984 times y, that comes from here, dy. Okay, so I'm just going to be able to use the power rule when I go to integrate these. So we're looking at 299 520y minus 9984 y squared all over 2, and I'm evaluating everything from 0 to 10. Okay, so I plug everything in, right, for 10 and 10, and I subtract out 0. So 9520 times 10 minus 9984 divided by 2 times 10 squared. And then if I plug in 0 for y, it's just going to be 0. So the total work that I need to do is 2496200 in my commas. And this is in units of foot-pounds. That's how much work is going to be required, okay, to basically pump this water out the top of our tank. Okay, and that's question 39. These kinds of questions where there's geometry involved are really common final exam questions. All right, let's take a look at question 42. This is another one that often shows up on a final exam. 42. Sorry, that's 2.9. 2.9, question 42. All right, so let's read the question itself. So 42 says, suppose we have a tank which is a right circular cone, and it has its circular base at the bottom. So what that means is it looks like this. I'm not a really great artist, but you get the idea. And here's my radius, and then here's the height. Okay, this base at the bottom, and it's a vertex at the top. Suppose that the radius of the base is 8 feet. So here's 8, and our height is 30 feet. Okay, the tank contains water up to a height of 10 feet. 10 feet. Okay, and the rest of the tank is empty. Find the amount of work required to pump all the water, they say to the top of the tank, but what they really mean is out of the top of the tank. Okay, so this is the drawing that we're going to be looking at here. Okay, so I've got my right circular cone with the circle at the bottom, and my radius at the bottom is 8, and the total height is 30. Okay, this is all in feet. And then there's water filled up to a height of 10 feet. Okay, so remember the height, right, from how much water we have from 0 to 10 gives us the bounds of integration. So let's remember, let's start writing things down again. So we're going to go from 0 to 10, right, because that's how much water I have. 0 to 10 gives you the bounds of integration. The force times the height. Okay, so force times distance integrated, right, is going to give us our total work. Because there are a bunch of things I need to be able to think about. Let's write down some pieces that we know. So the height, kind of like what we did in the previous question, the height is, my total height is 30 feet. Okay, but the water here at the top doesn't have to go as far as the water at the very bottom. So I need to be able to take into account a variable height. So I'm going to go 30, my total height, excuse me, minus where are we at currently in our y direction. Okay, now our force, okay, I need to think about, this is a circle, right? Our base is a circle. Now going up just a little bit higher is another circle, there's another circle, there's another circle. So the radius of the circles is like pennies stacked on top of each other. The radius of the circles is going to change as I go higher and higher. You can imagine the radius here is much smaller than the radius at the base. So my radius is going to change as a function of height. So I need to come up with an equation that's going to help me describe that. But let's first talk about the area of a circle. So this is pi r squared, right? And then dy, right? That's that tiny little sliver of thickness of this particular circle here, right? So this is basically our volume, right? So now I need to think about how am I going to come up with the radius? That's the big unknown. So let's think about that one. This is an arrow. So big unknown. So I'm going to think about similar triangles. Our radius is variable. So I need to come up with radius as a function of height. So the first thing I'm going to do is here's my, I'm going to draw like this cross-sectional area. Oops, I didn't draw that very well. Okay, so my radius at the base is 8. And my height in total is 30, okay? So now, depending on where I'm at, right, my radius is going to be x, right, because this is along an x direction, right? So this is x, and then, but where am I at? So whatever this is x, this height here is 30 minus y. So let's come up with an equation that's going to relate to these things here. So when my radius is 8, my height is 30, and that's equal to when my radius is x and my height is 30 minus y. And so I've got a couple variables here. So I'm going to solve for x. This is really my radius here. Okay, my x is equal to my radius. So if I solve for x, I cross multiply and kind of move things around. So I've got 8 times 30 minus y. I'm just going to leave it like that. I'll divide it by 30. Okay, and I can simplify this a little bit. So this is radius, I divide both by 2, so I get 4, 30 minus y divided by 15. You can just leave it like that. So this radius here is what I'm going to plug into pi r squared. Okay, so now let's write this out. So my f of x, pi r squared times dy, right? So I ultimately wanted this in terms of y because I've got this tiny little sliver of thickness in terms of y, the height that we're actually moving things. So let's write it pi r squared. So my r is 430 minus y over 15. Don't forget this whole thing is squared times dy. And that gives us the force. Okay? And then I need to actually multiply that by my density of water. Okay? So that's going to be our 62.4 pounds per cubic foot, which they gave us at the very beginning of this whole section here. So let's put it all together. So my work, right, we're integrating from 0 to 10. That's the volume of water that we're actually moving. Okay, so I'll put in my density function, so 62.4. I've got pi, my pi r squared. So 4 squared divided by 15 squared, 16 over 225. So all I did was square 4 and square 15. Right, and I've got 30 minus y, quantity squared, I'm going to leave it like that just for now, times my height, this is my height, times dy, this is my little sliver of thickness, right, that comes from our volume, okay? So now let's go ahead and start multiplying things through. So I'm going from 0 to 10, 62.4 times pi, 16 over 225, 30 times y squared times 30 times y, this is actually 30 minus y cubed dy. Okay, so now I can cube this whole thing out, right? Like I'm going to kind of, distribute all terms. So it's going to look like 30 minus y, 30 minus y, 30 minus y, right? I've got to multiply all these things out in order to get a long cubic polynomial. Then I can then just apply the power rule to it. But first, let's multiply everything through, like all of our constant terms. So 62.4 times 16 divided by 225 times pi. I'm going to pull those constants out. Okay, so this is 62.4 times 16 divided by 225 times pi, 0 to 10. Okay, so I basically multiply all these things out, and I'm going to get minus y cubed plus 90 y squared minus 2700, oops, I have an extra 0, 2700 y plus 27,000 dy. Okay, so watch your algebra here. Okay, and it's a negative, right, because I've got the minus y right there. So then it's just power rule. 9.8 pi over 225. Okay, my antiderivative, okay, when I do it, is minus 1/4 y to the 4th plus 30 y cubed, 30 y cubed minus 1350 y squared plus 27,000 y, and I'm evaluating this integral from 0 to 10. And now I'm just going to plug everything in, all the numbers, and I'm going to add everything up, and I'm going to combine it, and I'm going to get pi, or I can multiply through by pi, and I'm going to get okay. And that gives us the work. I think this is going to be foot-pounds. Okay, the work required to take this volume of water here and move it out the top of that cone. Okay, the kind of final exam questions you'll see when I post them online, we usually get like a cone question. Sometimes the vertex is at the bottom, okay, where it's like an inverted cone, kind of looks funny like this. And or the vertex is at the top. Always you need to be thinking about coming up with, the hardest part is coming up with some kind of a formula that's going to give you the change in radius as a function of height, like where you are at, okay, because your radius here is different from your radius here, which is different from your radius here. We need to have some kind of formula that relates that. This is usually the hardest part. And then the rest of it is just algebra plugging it in.